Our next speaker is Dr. Chip Fletcher. Dr. Fletcher is currently Associate Dean of Academic Affairs at the School of Ocean, Earth Science and Technology. I've known Chip for a long time. He's an accomplished scientist, teacher, author, and he's also a practitioner of his words. So he's one of the few, he's one of the few applied scientists in the university that I know that actually applies his work in the community. Chip is well known for his work in coastal geology and coastal sedimentology. I've known Chip for many, many years. Him and I were attached at the hip a few decades ago in trying to go around to raise the awareness of the importance of our coastal ecosystems and the importance of our beaches. We went to many, many meetings throughout the state, neighborhood boards, community associations, to try to spread the word about the importance of our coastal resources. Many times we were stoned and tarred and feathered, but ultimately I believe people began to listen to us, and so as a result of that, I think that is probably contributes to why we're here today. One of the reasons we're here today talking about this important topic. So with no further ado, Chip Fletcher.
Thank you, Sam. Thank you, Nainoa. I can't get my heart to quiet down. That was so generous of you to give this room the motivation and the sail plan for going forward and empowering us with your words. Every sail plan requires a lot of detailed analysis, a lot of study of what you're going to encounter, and my role is to help the Interagency Climate Adaptation Committee, along with the researchers in my team, Matt Barbie and Dr. Tiffany Anderson, to map out what future sea level rise may mean for our community. We know that 2015 broke all records as the hottest year in the last 130 years. We know that 15 of the last 16 years were the warmest years on record. We also know that climate change is highly variable, as you can tell from the patterns racing across this screen. That there is no place that is uniformly changing. There's no year that is uniformly warmer than the next. And so the science of climate change is demanding the very best research that is possible. So I want to begin the talk by reviewing some of the changes that are taking place and likely to take place both globally and here in Hawaii. And I want to touch on heat waves, changing precipitation patterns, food impacts, rain in Hawaii, ecosystem threats, changing storminess, optimism about climate change and why we should have it, and sea level rise for the second half of my talk. And each one of these many topics is worth an entire semester of a class in its own, and all I have time for is one slide per topic. So I want to briefly just do a quick survey of these issues. Heat waves. Heat waves are the most lethal form of climate change. 9 of the 10 deadliest heat waves have occurred in the last 15 years. We've lost 140,000 people to heat waves around the world. And models project that extremely high temperatures that historically were observed once every 20 years are likely to occur every 2 to 4 years by mid-century. Monthly global heat records have been broken 34 times in the last 16 years. Yet the last global cold record was set over 100 years ago, and the coldest year on record was in 1911. In Hawaii, high heat is stressing HECO. The grid is overloaded and those hot August and September days. And if you haven't been aware, the last 3 years, HECO has asked all of us to turn off our air conditioning at night because they can't provide the electricity demand that we're putting on them. This is clear evidence of heat waves stressing our grid. Yet all we hear about with regard to our electrical power system is how are we going to accommodate renewable power. This is extremely important. But heat waves are here right now. And as far as I can tell, Hawaii appears to be taking no action with regard to this. Imagine a high building where the electricity goes out and you are too young or too ill or too elderly to take 20 flights of stairs. You're trapped in a hot box. We need to start worrying about heat waves. Changing precipitation. Global drought has increased 10%, and global extreme rainfall has increased as well. A warmer atmosphere holds more rain. That's water that would normally be on the ground, and when it does rain, it tends to rain in intense fashion. We now have almost a weather-related disaster each day of the year someplace on the planet. This is 14% more weather-related disasters than we had a decade ago, and it's twice as many as we had 3 decades ago. These data come from the insurance industry, the keepers of our weather-related information. All of this has impacts on food. Research now shows global wheat provides 20% of the human protein on this planet, and yet higher CO2 levels that we're going to be reaching later this century decrease the nutrient and protein content of wheat. By 2050, demand for wheat will increase 60%, yet the actual yield is going to decline by 15%. Food prices are projected to double by 2030. Where are we? We are at the tail end of the global food distribution system. Local food production is critical. We play around the edges of this issue now. We try to buy local, we try to eat local, we try to go to local restaurants that use local food, but we need to get really serious about food production. And our food depends on irrigation. Rain in Hawaii is changing as well. Future rainfall is still unclear. We have a number of very talented groups working with modeling future rainfall, but we are a very small spot in the middle of the Pacific with very high topography that creates its own weather on a micro scale, and modeling this is extremely difficult. What appears to be coming out as agreement among the different modeling groups is that our wet season is going to experience decreased rainfall in the dry areas. We'll experience a longer and drier dry season. This will put greater demand on irrigation. We're also likely to experience intense precipitation. That is, when it rains, it tends to rain hard for short periods of time. Those intense rainfalls can overwhelm our drainage system. And this past September and October, we saw a couple of instances where Iwilei, portions of West Waikiki were underwater all day, and business had to shut down because the amount of rainfall falling was too great for the drainage system to handle it. Our drainage system is under-engineered. There are so many ecosystem threats. We're entering a new climate envelope. The range of high and low temperatures is entering territory that our ecosystems have never experienced before. Our ecosystems are especially vulnerable because they have evolved and grown into microclimates and microtopographic niches. Changing rainfall, changing climate, this is a perfect recipe for invasive species, those hardy species that can survive high variability in temperature and rainfall. And they're invading all of our ecosystems, from the reef up to the tops of our watersheds. This is also ideal for the spread of tropical diseases. And you all know we've seen dengue fever. We're all worried about Zika virus, chikungunya. These tropical diseases are now present, and they're spreading across the planet. Reef bleaching and ocean acidification. We've seen severe bleaching over the last 2 years in Hawaii, and NOAA last year announced its third ever global reef bleaching event. Storminess is changing for us and for the world. The tropics are expanding, and the zone of highest winds is migrating towards the poles, away from the equator. We are seeing a localized increase in rain intensity. Tropical cyclone paths are shifting to the north. Tropical cyclones that previously would pass south of the Big Island are now migrating into pathways that make the Hawaiian Islands more vulnerable. We see increased rainfall and wind speed associated with tropical cyclones. And models are calling for not only more El Niños in the future, but more strong El Niños, such as we've been experiencing in 2015 and currently. We had 15 tropical cyclones in the North Central Pacific last year. Our average is 4 to 5 tropical cyclones, and our previous maximum was 11. If you want a picture of the future, I think 2015 would give you a good idea of what our future will look like. There is reason to be optimistic about curtailing the worst of future climate change. Energy transformation appears to be solidly underway in the United States. In 2005, coal provided half of US power. That's now decreased by 16% and being replaced by sustainable energy forms. The Paris agreements in December provide a framework for global action. And compared to unchecked global warming, keeping the temperature rise below 2 degrees C as called for in Paris would reduce heat waves by almost 90%, flooding by 76%, cropland decline by 41%, and water stress by 26%. Sea level rise is something that's present, it's at our shorelines, and despite attempting to slow down climate change in the future, we might delay the worst of sea level rise, but it has a long memory. Last December, NASA said, given what we know now about how the ocean expands as it warms and how ice sheets and glaciers are adding water to the seas, it's pretty certain we are locked into at least 3 feet of sea level rise and probably more. Sea level rise causes coastal erosion, wave flooding, groundwater inundation, which means that in the coastal zone, the water table will rise as sea level rises. So it's not just about the ocean coming over the shorelines, it's also about new wetlands forming behind the shoreline where we live. And drainage failure. Hurricane and tsunami vulnerability also increase as sea levels rise. We know that sea level has been accelerating from around 0.5 millimeter per year early in the 20th century. It doubled as an average over the 20th century. It's doubled again in the era of satellite measurements. And the last paper I saw last year placed global sea level average rise at 4.4 millimeters per year over the short term of the record, the most recent shortest phase of the record. The scientific literature is filled with projections of how high sea level will rise by the end of the century. On the far right of the screen is guidance provided by the U.S. Army Corps of Engineers and NOAA. This guidance is the result of analysis of peer-reviewed literature and expert testimony, largely coming from the National Research Council, which is the next 2 estimates coming in from the right to the left. Horton in 2008 projected sea level rise by the end of the century on the basis of expert testimony. The next cluster of Katzmann, Jevrajiva, Vermeer, Pfeffer, and Rahmsdorf are referred to as semi-empirical models. They project the future of sea level based on the relationship between temperature and sea level as observed. But only the IPCC in 2001 2007, and 2013 use the fundamental laws of physics and our best understanding of how ice sheets are behaving and how the oceans are storing and reacting to heat to project future sea level. So for the modeling that our research group in SOAST is doing for the Interagency Climate Adaptation Committee, we're adopting the sea level projections of IPCC Assessment Report 5. Now looking at the forest of projections here, we might be cutting short. We might be shooting too low. Sea level certainly may be much higher in our future. This graph shows in orange the business as usual projection of sea level if we continue to burn fossil fuels without concern. In purple, it shows what most technicians believe is an unreasonable opportunity. We are not likely to reach it, but it would be great if the human community were able to decrease our burning of fossil fuels and replace our electricity needs with sustainable sources. We chose the outer band of that worst case scenario. This is our model of sea level rise in the erosion and flooding scenarios I'm going to show you next. One reason for doing this is because the tropics are, for gravity, geophysical reasons, the tropics are going to be experiencing 10 to 20% greater sea level rise than the global mean. And you can see us right over here. Looking at the geological evidence and the modeling evidence, we know that sea level is not going to stop at 2100. It's going to continue rising for centuries. In fact, 2015 reached 1 degree C of warming above the pre-industrial revolution temperature. And modeling and geologic evidence tells us that sea level will not stop until it's reached over 10 feet above the pre-industrial level. By 2 degrees C, which is that temperature that we hope Paris will be able to enact the guidelines in Paris and stop global warming, sea level is going to continue rising for many meters above that. So what will the ICAC report look like? There are many reports from most coastal states. In New York, they looked at the problem of storm surge under higher sea levels, and they mapped communities that would be vulnerable to sea level under storm surge, as well as what is known as static sea level rise. They take basically a topographic model and they raise sea level and they see what areas lie underwater at that higher sea level. This is called static sea level rise. In San Francisco, they looked at the 100-year flood and they also mapped static sea level rise. In Delaware, static sea level rise. In Los Angeles, their adaptation report for future sea level is to look at storm surge and static sea level rise. And California Coastal Commission provided policy guidance on how to adapt to these problems. We wanted to go beyond these precedents, and so with our committee, we are modeling static sea level rise, groundwater inundation, coastal erosion, seasonal wave inundation, as would be seen by our expected annual seasonal waves, not storms, and 100-year coastal flooding. I want to call out Matt Barbie. Matt, are you here? Matt's taking care of his young son, no doubt. And Tiffany, would you please stand up? Oh, where are you, Tiffany? Tiffany's in the back of the room. Tiffany and Matt are the ones who are doing this modeling. Our first modeling was in the EVA region. What you see here is a grid of the wave model that we use. We're forced to model, because of time constraints, waves as if they were in a flume. That is, they don't interact with each other, and so we get no wave diffraction or refraction or reflection. This is called one-dimensional wave modeling. You simply run a wave up on the shoreline, and 20 meters next door you run another wave, and they don't interact with each other. This region in particular, Eva Beach, we're all familiar with Eva Beach. It's seen 50% growth in population over the last decade and a half. It consists of a narrow, chronically eroding beach backed by seawalls and single-family homes, most of whom are built slab on grade. That is, they are built right at ground level and not on post and pier. That is, there's no freeboard underneath these homes. We use microtopographic data acquired by LIDAR, collected by various federal and state agencies, and we extend our digital elevation model with bathymetric mapping from the University of Hawaii. Here's our digital elevation model. You're looking at a topographic model. You can see the microtopographic features offshore on the fringing reef surface, and you can see the footprints of the roads and buildings on the topographic portion, the landward portion. So we use that modeling to project future erosion and future wave inundation. This is static flooding and groundwater inundation under our 3.2 feet at the end of the century, and you probably can't see any difference. There's one little green spot there where we predict that the groundwater table will rise and create a new wetland. But other than that, all this modeling shows is the water creeping up on the edge of the beach. Because when you stand on the beach, you're more than 3 feet above sea level. So there are no dynamics or physics in this type of modeling, and it vastly underestimates our vulnerability. There's 4 feet of sea level rise, only 25% more sea level rise. And this points out what we refer to as the critical point. So in green are regions not connected to the ocean, but they're likely to be flooded by the groundwater table. And in blue are regions that are connected to the ocean, and they're likely to be flooded by the ocean. The critical point turns out it's that topographic region between about 3 and 4 feet, where as waves run up the shoreline under rising sea level, they do small increments of increasing damage until they breach this critical topographic elevation, and then there's enormous flooding that takes place. In fact, it's a paper by Haunani Kane and our group that identifies this critical point. Regarding erosion, Tiffany published a paper last year, Doubling of Coastal Erosion Under Rising Sea Level by Mid-Century in Hawaii. She looked at 10 areas on the islands of Kauai, Maui, and Oahu, and found that 92% and 96% of shorelines in these areas are projected to retreat by mid-century and end of the century, respectively. 80% of the projections she modeled range up to 80 feet of erosion by mid-century and 200 feet of erosion by end of the century. View those numbers in the context of our setback, which is, as a state law, it's roughly 40 feet. This is twice extrapolating historical erosion rates. So what we do in our erosion modeling is we determine historical rates of shoreline change, and we use historical shorelines as mapped from aerial photographs going back to the beginning of last century. We take these shoreline positions and model their long-term change, and then we can project that long-term change into the future. But that's assuming that what's happened in the past is going to happen in the future. In other words, it's basically extending our past sea level into the future and assuming a very small amount of sea level rise by the end of the century. So we need to account for sea level rise as modeled by the IPCC. And to do this, we add an additional element, which is basically defining the profile of equilibrium across a beach and migrating that as sea level rises, assuming that the shoreline stays in equilibrium with where sea level is located. So we add these two together, and we project forward our estimates of future sea level rise, future erosion. What this does is take into account the high variability of our shorelines. We have areas that are accreting and areas that are eroding, and that variability is taken into account in our modeling through the aerial photograph analysis. There's our 80 percentile erosion boundary by the end of the century. The green line, which you can barely see, I know, is the modern boundary of the beach. We project 80 percentile erosion probability lines for the end of the century and for the years 2075, 2050, and 2030. Regarding simulating wave inundation under higher sea levels, we all know that Hawaii has a complex wave environment. And so from each location of our shoreline, each exposure of our shoreline, we need to characterize the mean wave climate, and we use what's known as the significant wave height to do this. And as I mentioned, our modeling is simply one-dimensional. We run a wave along a transect into the shoreline, and we do this every 20 meters around the island. This is an underestimate, most likely, of the threat from wave inundation. For the South Shore, for instance, we chose a typical southern swell coming in from the southern hemisphere in the summertime, a significant wave height of 2.3 meters in a period of about 16 seconds. We use the highest water levels flooded by our model and create a grid of these, a GIS layer, and we turn them over to Tetra Tech, our consultant, who then counts buildings and infrastructure that are in the way of this water. So here's our present day estimate, testing the model, showing that under typical southern swell conditions, the waves basically run up against the seawalls to the end of the beach. Our model is calibrated in that regard. By 2030, with 17 centimeters or half a foot of sea level rise, we see some minor flooding happening over here to the west of the beach itself. By 2050, we're starting to see this flooding do some serious damage to a handful of homes, roughly a dozen homes. As we move towards the middle of the end of the century, we're looking at upwards of 100 homes experiencing this flooding. And at the end of the century, we see dramatic flooding taking place. Now, we have not yet crossed the critical point. We're still at 3.2 feet above sea level rise. If we go to 4 feet of sea level rise, which we eventually will, it's a catastrophic situation. How you build your home, how you build your roads, how you plan for living in these communities, these are all things that we need to think about. The old way of doing it won't work. And I'll end with this. This is a model result for the North Shore. We start just to the east of Haleiwa. You're looking at wave flooding at the end of the century under 3.2 feet of sea level rise. In the blue, in green, you look at groundwater inundation, which is going to occur in our lowest lands. Generally speaking, the North Shore is a higher elevation than many other areas and many other coastal regions on the island. But there are places, if you saw the news this morning, last night, we saw the region near Ehukai flood in last night's high tide. And you can see that the flooding takes the first row of houses and in some places back to the road. Now, if you can see the red line, that's our erosion model. So if we were to do this properly, which we hope to do, given more time, we would be flooding the waves from the red line, right? If the shoreline is going to be relocated by erosion, that's the point where the waves would flood. But again, because of time constraints, we've had to model the wave flooding from our current shoreline, but we can project in the red line the 80 percentile probability of erosion in the red line. As we turn the corner and come down the windward side of the island, you can start to see the general elevation of the coastal plain lowers, and we see a lot more groundwater inundation taking place in green. This also points out the very localized nature of the hazard. There are entire communities that are vulnerable to flooding, and there are entire communities that appear not to be. One of the assumptions that has gone into this is, and it's a very important assumption in wave modeling, is the friction factor. To what degree will the wave interacting with the reef change the wave characteristics? And we've had to make a broad assumption. We've taken the NOAA bathymetric habitat maps, and we've assigned friction values to every one of the different habitats. But we'd like to actually go out and do the field work to directly measure and calibrate our model with real-time measurements of run-up and wave height. So it's not we have to run to the hills. It's that we have to adapt, and we can do it locally. We can give some broad policy guidelines, but really it's individual communities that need to come together and think about, this is our future, what can we do to become part of our future, to take responsibility and take charge of our future? It's not all up to the state and the county and the feds. Communities have to get involved, because the communities really know best about how to manage themselves and how to manage their lands, because they know those lands better than anybody else. We're coming down the windward side, and we're going to turn into Kahana Bay, and we're going to end with that. Thank you very much.
Thanks, Dr. Fletcher.